Hello everyone. Today we are going to analyze this frame using stiffness matrix method. Before analyzing, let us see the frame one time. In this frame, there are two columns, column AB and column DC, and there is a beam BC. This frame is symmetrical in the dimensions. Also, the loading is symmetrical. So, this is a non-sway type frame. The columns carry point loads 20 kN in the centers. The beam carries uniformly distributed load 15 kN per meter acting for the full span. The length of the columns is 4 meter and the length of the beam is 5 meter. The moment of inertia for the columns is given as 2I and for the beam it is I. Now let us find the fixed end moments. In the column AB, there is a point load 20 kN acting in the center. The formula for the fixed end moments are minus WL upon 8 and positive WL upon 8. Using the formulas, we can find the fixed end moments M of AB and M of BA. Now let us take the beam BC. In the beam BC, UDL 15 kN per meter is acting for the full span. The formula for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. Using the formulas, we can find the fixed end moments M of BC and M of CB. Now let us take the column CD and find out the fixed end moments. In the column CD, there is a point load 20 kN acting in the center. The formulas for the fixed end moments are minus WL upon 8 and WL upon 8. Using the formulas, we can find M of CD and M of DC. In the stiffness matrix method, we have to find the kinematic indeterminacy. For that, we have to check the supports and the joints if there is any deflection or slope. In the points A and D, there are fixed supports. In the fixed supports, there will be no slope and deflection. In this frame, we have two joints, joint B and joint C. In these joints only, the beam and the columns are connected. Since this frame is a non-sway type frame, there will be no deflection in these joints, but there will be slope. So, the kinematic indeterminacy of the frame is 2. In the joint B, we have the slope theta B, and in the joint C, we have the slope theta C. Now, let us make the fully restrained structure. We know that in the joints B and C, there is slope, but in the fully restrained structure, there should be no slope and deflection in the joints and the supports. So we have to apply fixed supports in the joints B and C. You can see that I have applied fixed supports in the joints. Now in this structure there will be no deflection and slope in the end supports and the joints. That is why it is called fully restrained structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. The coordinates are in the points B and C because in these points only we have the slope. The coordinates should be made in the clockwise direction. Now let us see the formula to find out the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix. Inside the delta matrix, we will have the slope values theta b and theta c. Inside the PL matrix and P matrix, there will be two values because in this analysis there are two coordinates. K is the stiffness matrix. The size of the matrix will be 2 cross 2 because in this analysis there are two coordinates. P matrix is the final forces acting in the coordinate direction. In the given frame, there is no overhanging. So inside the P matrix, we can simply enter 0, 0. So in this formula, we have to only find K matrix and the PL matrix. We know that PL matrix is the moments developed in the coordinates due to the given load. In this analysis, there are two coordinates. The coordinates are in the point B and in the point C. The first coordinate is in the point B. In the point B, we have found two fixed end moments, M of BA and M of BC. We have to add both of them. After adding, we are getting minus 21.25. Our second coordinate is in the point C. In the point C, we have found two fixed end moments, M of CB and M of CD. We have to add both of them. After adding, we are getting 21.25. In this formula, we have found PL matrix and the P matrix. Now let us make the stiffness matrix. Let us see how to calculate stiffness matrix elements. First, we have to apply unit displacement in every coordinate. In this analysis, there are two coordinates. The coordinates are in the points B and C. So in these points, we have to apply the unit displacement. Then we have to use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. We have to be very careful. We have to apply the unit displacement in the fully restrained structure and not in the given frame. In the stiffness matrix, now we are going to find the first row. For that, in the first coordinate, we have to apply unit displacement. In the point B, there is a fixed support, but when we apply the unit displacement, it becomes hinged support. We have applied unit displacement in the point B. You can see that previously there was a fixed support, but after applying the unit displacement, it became a hinged support because in the fixed support there will be no displacement. Now let us see how to draw these curves. We are applying unit displacement in the point B in the coordinate direction. We made the coordinates in the clockwise direction. In the same clockwise direction, we have to apply unit displacement. The point B is a joint. It is connecting the columns BA and BC. So from the joint B, we have to make two clockwise curves. One curve towards the point A and one curve towards the point C. Then we have to see the direction of these arrows. This arrow indicates on the left side, so the curve comes on the left side. This arrow indicates downwards, so the curve comes below the span. In the fixed supports, there will be no slope, so we have to give some gap between the curve and the fixed supports. In the stiffness matrix, now we are going to find K11 and K12. K11 and K12 should be represented in the clockwise direction because we have made the coordinates in the clockwise direction. K11 should be calculated from the point B because that is our first coordinate, and K12 should be calculated from the point C. Now let us find K11. For that, from the point B, we have to look on the other ends. In the end A, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Here the moment of inertia is 2I, so instead of I we have to apply 2I. Length of BA is 4. Let us apply that. Now let us look on the other end C. In the point C also there is a fixed support. So we have to apply the same formula 4EI upon L. Length of BC is 5. Let us apply that. For K11 there are two values. We have to add both of them. After adding we are getting 2.8 EI. Now let us find K12. For that, from the point C, we have to look other ends. In the point D, there is a fixed support, but there will be no stiffness because for CD, there is no curve. Now let us look on the other end B. In the point B, there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of CB is 5. Let us apply that. Finally, for K12, we are getting 0.4 EI. In the stiffness matrix, now let us make the second row. For that, in the second coordinate C, we have to apply unit displacement. In the point C, there is a fixed support, but when we apply unit displacement, it becomes a hinged support. You can see that I have applied unit displacement in the point C, so the fixed support became a hinged support. Now let us see how to draw these curves. We are applying unit displacement in the point C. From the point C, we have to make two clockwise curves, one curve towards the point B and one curve towards the point D. Then we have to see the direction of the arrows and draw these curves. We have to be very careful. We should give some gap between the fixed support and the curves. Now let us find the values in the second row K21 and K22. K21 should be calculated from the first coordinate and K22 should be calculated from the second coordinate. Let us find K21. For that, from the point B, we have to look the other sides. In the point A, there is a fixed support, but for BA, there will be no stiffness because there is no curve for BA. Now let us look the other end C. In the point C, there is a hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. Length of BC is 5. Let us apply that. Finally, we are getting 0.4 EI. Now let us find K22. For that, from the point C, we have to look on the other ends. In the point B, there is a fixed support. If the fair end is fixed, the formula for stiffness is 4EI upon L. Length of CB is 5. Let us apply that. Now let us look on the another end D. In the point D also, there is a fixed support. So we have to apply the same formula 4EI upon L. For CD, the moment of inertia is 2I. So instead of I, we have to apply 2I. Length of CD is 4. Let us apply that. For K22, there are two values. We have to add both of them. After adding, we are getting 2.8 EI. In the stiffness matrix, we have found both of the rows. Let us apply them. For K12 and K21, we will get the same value. EI is constant, so let us keep it outside. In this formula, we have found everything. Let us apply them. We can add these two matrices. After adding, we are getting this. EI inverse is 1 upon EI. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find the inverse of a 2 by 2 matrix, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and found the inverse. Then we have to multiply these two matrices. After multiplying, we are getting these values. In this analysis, we have found the unknowns theta b and theta c. Now let us make the slope deflection equations and find out the final moments. First, let us make the slope deflection equations in the column AB. In these equations, let us apply the fixed end moments. For AB, the moment of inertia is 2I. So instead of I, we have to apply 2I. Length of AB is 4. Let us apply that. In the point A, there is a fixed support. In the fixed support, there will be no slope. So theta A will be 0. After applying the value of theta B in these equations, we are getting MAB and MBA. Now let us make the slope deflection equations in the beam BC. In these equations, let us apply the fixed end moments. Length of BC is 5. Let us apply that. After applying the values of theta B and theta C in these equations, we are getting MBC and MCB. Now let us make the slope deflection equations in the column CD. In these equations, let us apply the fixed end moments. The moment of inertia for CD is 2I. So instead of I, we have to apply 2I. Length of CD is 4. Let us apply that. In the point D, there is a fixed support. In the fixed support, there will be no slope. So theta D will be 0. After applying the value of theta C, we are getting MCD and MDC. For MAB, we have got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we have got a positive value. That means it is acting in the clockwise direction. For MBC, we have got a negative value. That means it is acting in the anti-clockwise direction. For MCB, we have got a positive value. That means it is acting in the clockwise direction. For MCD, we have got a negative value. That means it is acting in the anti-clockwise direction. For MDC, we have got a positive value. That means it is acting in the clockwise direction. Now let us find the reactions. First, let us take the column AB and find out the reactions. We can find out HA when we take moment about B. Then we can apply the rule sigma H is 0. Using the rule, we can find out HB. Now let us take the beam BC and find out the reactions. Here there is no need to take moment because this moment and this moment is acting in the opposite directions. They will get eliminated. So no need to consider these two moments. This is UDL. When we multiply the UDL with the distance, we will get the total load. When we divide the total load by 2, we will get RB and RC. Now, let us take the column CD and find out the reactions. To find out HC, let us take moment about D. Finally, we are getting HC. Then, let us apply the rule sigma H is 0. Using the rule, we can find out HD. Now, let us make the shear force diagram. Using the loads and reactions, we can make the shear force diagram in the column AB. Then let us make the shear force diagram in the beam BC. Then in the column CD. Now we are going to draw the bending moment diagram. For that, first we have to make the free movement diagram. For the free movement diagram, we have to assume all the spans are simply supported beams. Using these formulas, we can find the moments. Then, using the direction of the end moments, we can draw the end moment diagram. Then, we can combine the free movement diagram and end moment diagram so that we will get the bending moment diagram. Now, we are going to end this session. Thank you for watching this video.